Thank you. Yeah, welcome. Thanks for having me. I'll do a proper screen share in a second, but the second slide doesn't want to show, but I want to show you my group in a second as well. So that's why you have to keep with the weird modus at the moment. I'm going to present a bit about what we're doing in our research for like 15 minutes or something. And then I've prepared a Colab notebook and we can do some coding, especially for forecasting energy time series. And I hope it's going to be interesting for you as well. Okay, this is my group. And we're relatively new. I started in Tübingen 3 years ago. Most of these people started last year. So I'm really excited that we're now forming this little group up the hill in Tübingen and looking into machine learning for sustainable energy systems. Yeah. So what do we mean when we talk about machine learning or AI for sustainability? Basically, we want to implement new algorithms or come up with algorithms that help us to achieve these goals. These are the UN Sustainable Development Goals. There are 17 of them in total. And it's sort of the United Nations version of a better indicator for progress instead of the GDP, which usually is used to measure the progress in a country, and the UN's thought, no, that's a bit stupid. We don't want to just look at economic progress. Why don't we have these 17 goals? And in our group, we believe that machine learning can help us, especially help the decision makers to make the best decisions to achieve these goals. None of us really believe that machine learning solves any of the issues that are addressed by these goals. And what's probably also quite interesting to realize is that machine learning also harms or can harm some of these goals. So we're not, just because we can use machine learning doesn't mean we can automatically do something good, but we can try. 17 goals is a bit much for a tiny group that we are. So at the moment, we're mainly focusing on affordable and clean energy, climate action, a bit on sustainable cities, and we've had some projects on clean water and sanitation, but also just a tiny aspect. Why is it interesting to look at energy in particular? Why have I brought an energy data set and hope we can do some energy forecasting? How we use and produce electricity contributes massively to our CO2 budget. As we can see here in this graph, this part here, electricity, that's about 25% of all our carbon emissions. So what we do here has quite the impact. But unfortunately, electricity or how we use it doesn't only show up in this quarter over here in this, but it also comes up in transport. If we use electric vehicles, then that's also somewhere where we use electricity. It comes up a bit in how we use the buildings that we have. How do we do cooling and heating of them especially? And it can also come up in heavy industry. So how we use and produce electricity, quite relevant when we want to mitigate or adapt to a changing climate. Now, the core solution from an electricity systems perspective is, let's use renewable energy that's carbon neutral, at least as soon as all of the power plants are there. And if we electrify everything that we can electrify, then we can produce our electricity carbon neutral. We know how to do that. Unfortunately, it's not, we can't just build up lots of power plants and then we're done. We don't have the space to just randomly pop up lots of wind turbines and then hope for the best. the issue that we have is if we think that this is our demand, then what we used to do in the past and still mostly doing today is use the coal power plants and the nuclear power plants and whatever you have around to match this demand curve and actually produce a bit more just to be sure. Now, with renewable energy systems, we can't do that any longer. We suddenly have a supply curve in red given by these renewable energy sources, and we can't just tell the wind to now blow a bit stronger or the sun to shine some more hours, at least not yet, and hopefully never. But what we can do is we can look at the demand side of this graph, because we know what's going on there. This is like industry using their robots or us turning on a coffee machine. Each of this contributes to this demand block. And one of the exciting things that we are also working on is what do we have to do to shift how we use electricity in order that it fits better to what is available from renewable energy sources. So what we need to go from, oh, we have demand that's unchangeable to, oh, we use energy whenever it's actually available, is we need to know exactly what the renewable energy sources that we have will produce at a given point in time. We need to know how much we want to consume, and we also need to know how much could we change what we consume. Like, my standard example is if you want coffee in the morning, you will probably just turn on the coffee machine and not wait for 2 hours until the sun is up, so you can then have a coffee. But on a larger scale, if you look at industry, that 2-hour shift of like a process that needs a lot of electricity could actually have a really big impact. So if we know that we can shift the process by 2 hours, and we know 2 hours later there's going to be sun or wind or whatever resources you have, then that is actually awesome and we can use it. So yeah, the household example is, yeah, there's some appliances in your household where you would probably be totally fine moving their usage for 2 hours. Most people don't care when their washing machine runs, as long as it runs at some point or is done by a specific point in time. Also, one of my favorite examples is my parents have PV panels on their household rooftop by now, and since they have these PV panels, the dishwasher always runs over noon. Because they saw the spike in the data when it was running in the evening, and they had lots of energy they could use over noon. So now the dishwasher always runs at noon, at least in the summer. In the winter, sometimes it just doesn't. There's just no sun available. Yeah, so in the group, we care a lot about what's the relationship between weather, climate, and the energy system. Most importantly, we're thinking about how uncertain are we, so we don't just want to forecast the power for the next day, but actually know how certain are we that we're going to get that amount of power. And to come back full circle, the renewable energy systems rely on the weather, and if we have a change in climate, then the weather changes, so how we can use electricity changes again. And if we go, if we mitigate climate change a bit more, then we can use more renewable energy resources. Wind is one of the best examples. Wind power is probably going to go down with a changing climate, but if we mitigate climate change a bit more and stick to, I don't know what the path is at the moment, let's say 2 degrees, then we can use more wind power in the future. Yeah, what are other projects we're looking at? The group is quite diverse. We're doing some intelligent control and fault detection in solar thermal systems. So solar thermal systems are, in contrast to PV, they heat up your water. So they're mostly used for hot water usage and for heating purposes in the home. They're really cool, but there's not enough knowledge available for these systems for just regular people to fine-tune them. So we hope that with some automated analysis, we can help. I've already talked about the shifting of the demand when renewable energy sources are available. And we are trying out some reinforcement learning to learn how to shift the processes in our homes. On a much larger scale, we're interested in the question like, well, what should the optimal energy system actually look like? And that depends a lot on what's currently already there from like a power system network perspective, and where could we enhance it? Where would you put new transmission lines? Where to put your solar resources? And questions like, does it make a difference if we optimize for Germany or Europe, for example? Or can we, if we optimize for Europe, can we use the same knowledge to optimize South Africa? The answer is always no. So that's why we're really interested in getting data from from as many countries as we can to see their specific needs and challenges. If you would optimize the European transmission system, so the European power system instead of the German one, we could save lots and lots of money. But unfortunately, that's a political decision. Machine learning can't help with that. We're doing some time series forecasting. The interesting bit is here how to get the weather that is inherently uncertain as well, how to get that uncertain information into our forecast and then do proper forecasting without our uncertainty measures blowing up on us, just not knowing anything at all. We have a physical system, like energy systems are built by human engineers, so there's knowledge in them. And then the question is, can we extract that knowledge, or should we just discard that knowledge and run a large language model and it'll do anything we want? And then lastly, as I already said, we're looking into climate change impacts, and there specifically the question like, what does climate change mean for very local points in, for example, a single wind turbine? If we put up a wind turbine now, it has a lifetime of around 30 to 50 years. So it will definitely see a change in climate, and it will definitely, its output will definitely change. And we're interested in quantifying by exactly how much. Yeah, that was it for the very short introduction. And this is how you can access the notebook. Yes. Yeah. So the question is, can't we just save the energy? So store the energy somewhere and then use it whenever we need it? That, in our sense, falls under demand side management, because we have a consumption at the point where we wouldn't have a consumption without the electricity storage, and then we have something where we supply electricity again. But yeah, that's part of it. Yeah. But if we would only rely on storages, then we would need massive storage, and we can actually do both. We can store a bit of the
Google Drive that we get from display is protected, and you don't have
Does anyone know how I can give you access?
Sure.
Maybe now. Yeah, so I realized I shared the solution with you, unfortunately, just kind of 10 minutes before we started. So there's almost everything is already in that notebook. but you can use it as a resource. And I hope we can play around a little with it together. So the solutions are almost all in there. You don't need any Python knowledge whatsoever, but we can have a look together. I can explain what I'm doing and why I was doing it. That's maybe more interesting. And then you can use the code as a resource, hopefully, if you ever want to do something similar. It's basically the name of the summer school 2023.
I'm sending them to you.
Awesome.
I got it.
So yeah, the data is in a Dropbox folder. You can reuse that data for your own purposes if you want to. It's not like public, as in I haven't published it anywhere, but feel free to use it. So yeah, I just load the data and it doesn't work. Awesome. Yeah, okay. Yeah, I have to load all the libraries, obviously. Okay, so in this data set, what you have is like the measurements that one household PV system measures over, in this case, it's a year from mid-2021 to mid-2022. What you can see is the production. This is what the PV panel produced. Purchased is what the household purchased from the grid. So all of the electricity that couldn't be provided by the PV panel. Feed in is what the PV panel feeds back into the grid. So all the electricity that the household didn't need, but was still available from the PV panel. Consumption is the overall consumption of that household, electricity consumption. And self-consumption is just the part that the household got from the PV panel. And that's all the relevant variables. There's only dates. In this system, whenever it's, not always, but most of the time when it's 0 and there's no electricity flow from the PV panel, then it puts a none there. In the original data, it's just empty. So in order to work with it properly, we can just fill all of these nuns with zeros and nothing happens because there's actually 0 electricity at this point. And
because Nicole, I think you need to upload something again. Right?
Yeah.
Just a question on understanding PV panels in general. For example, subject 8755, they created a bunch, but then they only bought some. So it's one line, couple of lines.
Yeah, so sorry, I didn't say that. So this is just one panel and over the whole time period. So it's these are the numeric time steps. So it's time step 1 to 8,760, so it's exactly a year. So at this timestamp, for example, in May 2020, in the evening, there was lots of production still. But yeah, it also says purchase because this data here is hourly. So during that hour, that was the amount of electricity that was produced. But during that hour, at some minutes, there was a mismatch. So there's probably one cloud or just someone was running the washing machine and was a tiny bit above what was produced. Yeah. So that's why they don't match exactly. If we look at the time series, This is like a plot of all of them. And what you can nicely see already is they obviously line up. So if there's lots of production, then there's not so much purchasing. Then here in winter, there's not so much production at some days. So you have to purchase a lot more electricity. It's not zero most of the time because there's a constant base load of this household. So some things like refrigerators, freezers, plugged in televisions and stuff, they're always running. So it's almost never, the consumption is always never exactly zero. What you can also see, which is quite nice, is that just because it's winter doesn't mean there's no solar production at all. It doesn't need to be warm for electricity to be produced by these panels. It just needs to be sunny. Their efficiency decreases in hot weather. So above 25 to 30 degrees, their efficiency drops. So even for solar panels, just hotter weather every day, increasing temperatures is not super cool. Yeah. They're also less efficient at like freezing point. And in some, when it snows, I think, I don't think in this year there was snow on the panels, but when there's snow on the panels, there's no way to clean them, to clean the snow off. So you have to wait for the sun to melt the snow from the panels. And there's also, in this area of Germany, there's sometimes something called the Sahara dust. So there are meteorological events like these Sahara dust waves where small sand particles are in the air, and they, so the sun rays can't hit the panel as if these small particles weren't in the air. So these meteorological events kind of decrease the efficiency of the panels. Apart from them, it's basically just if it's more cloudy, there's less energy, and if it's less cloudy, there's more energy. Yeah, if you want to, the next plot just shows this on a like smaller time scale, so you can see the exact patterns there. And you can also see that if this household would know when the sun goes down exactly and how the electricity should be used, then maybe they could, get rid of these very tiny inefficiencies where like half an hour earlier they would have had the energy to supply whatever they wanted to do there, but then half an hour later, there's not enough electricity available. What you can also see here quite nicely is that at least in summer, there's lots of times where the production is higher than self-consumption. The cool thing about time series data, and especially these, what you can already see is that they're kind of very, very regular. In the sense that there's definitely a daily pattern there. There's definitely might also be some weekend pattern or something. So what I do with these, like with this block here, is I create some new variables based off the time features that we have in order to include those into the forecasting. And if you want to have a closer look in how these patterns actually look, this is, if you just plot every day over another. Yeah. Yeah, so in this data set, I mean, it's mid-2021 to mid-2022, so it's most of the lockdown stuff is already over, I would say. Yeah, in this household, both people in this household are at home. It's just one household. And in this case, they are at home over lunch and they use it for cooking, and they have an electric oven or stove. So yeah, I have other data from Mexico City, which I found really interesting, and there this lunch peak was not there whatsoever, but starting at 8 p.m. It was a bit higher, but the whole consumption wasn't as high because in Mexico you usually don't cook with an electric stove, but you have a gas oven and stove. So this is very European, Germany-centered data, and that's why it looks like this. Yeah.
Maybe the previous visualization, because we put something in there, and when you look at certain consumption, I think that but the house from the energy that and it aligns to the moments where the production is happening, right? But the other one, church, what exactly doesn't mean, because that one happens with exactly none of them.
Yeah, so the purchase is sort of whenever the household wants to consume. So what's missing here, maybe that's also a bit, maybe I should have put that in. The consumption, the overall consumption is not shown on the graph. So the purchase here is whenever they wanted to consume electricity, but it couldn't be provided by the red line, because you can see that here the red line is already below what they wanted to consume apparently. And then the yellow line is what they needed from the grid to get to their consumption.
Yeah, I think it's good that it's not like a total consumption, because it would be exactly like the blue graph and the yellow graph.
Yeah. So you probably can't see anything at all. Yeah.
In that case, the idea is to align the taking place, right? But then that also means, for example, when you have a consumption that is somehow actually happening when what's energy is being produced. So what does it mean? Like, do the person and buy the moment to non-pretty and cook and do the whole
Yeah, so the idea would kind of be that you want this, for example, this peak here, the yellow peak, you want that to be shift a bit before and add to so that you can add to the blue, if that makes sense. So you kind of want as little of the yellow outside of the red area, the red curves as possible. If you say your aim is to be, for example, autonomous or only rely on the PV panel. Now, most of the electricity is fed into the grid. And this is also a bit of an issue for the people controlling the grid, because they kind of have to do forecasts to know what's coming in. But it can also be really useful and stabilize the grid at moments where it otherwise would need backup power from somewhere else. Yeah. Oh, I don't think I have bar charts anywhere. Does anyone else? Okay. Maybe you can show me later and I can tell you. Yeah, we can do the same thing. What I plotted here was the consumption. And what I plotted down there is the production, and you can see that these daily patterns that you have nicely have in the consumption, they're obviously ridiculous in the production because the sun does not care whatsoever which day of the week it is. But what you can also see nicely is that if you aggregate all of the values, it's actually a really, really smooth curve. But you have to aggregate to get there. What I did in this, or in the rest of the notebook, what you can already see, I've implemented some methods, a very basic linear regression and simple neural network, a recurrent neural network, more specifically a long short-term memory machine, and then a decision tree in random forest, and then compare sort of all of these methods to each other and how they perform. Spoiler alert, it's not the LSTM that performs best. We start with a linear regression, and one of the features that are usually quite helpful in all of these very autoregressive time series, so meaning that the last day or the last hour is very similar to what's happening now, are these lagged values. So I basically, in this case, used consumption and production, but you can also try out whether it performs better if you use the lags of self-consumption or of the feed-in or whatever. That's just how you do it. I used a shift. This is hourly data, so this makes absolutely no sense here in the middle. Awesome. So lag consumption and lag production, this here is the previous time step as it's hourly data, that's 1 hour. So we can do maybe that's why the results were not so good. So what's usually in energy time series really nice is like you take the last hour's value because the weather usually doesn't change super quickly. So last hour's value is very good. Also, with respect to our consumption, that can change a lot during an hour, but it's still, during some hours, it will just remain very stable. What's a really, really good estimate is kind of what happened the previous day. We saw that most of these days look super, super similar. So we always have this peak at 12 noon. So knowing what happened the last day at 12 noon should help our model a lot. And then we also have these weekly patterns that we've seen a bit. So in the Saturday, Sunday, I think I didn't talk about it too much here, but Saturday and Sunday, the green and blue curve here, they're a bit lower than all the others and they're a bit higher later. And they especially start the day later. So people sleep in a bit on Saturday and Sunday. But no, we can use this knowledge to feed it into our model. So what I do here is just take the value from 168 hours ago, that's exactly 1 week ago, and maybe use that in a model. Because Python's linear regression method cannot work with missing values, I just throw out the first 168 rows so that we can, that's then the first day where we actually know the value from a week ago. And then we can check that this looks reasonable. So we now have these, oh yeah, that was now obviously not so smart. Okay, so there should be one leg one sort of last hour, then one for the last day and one for the last week. And if you, oh no, this is, yeah, now I have to do this again. And that looks, yeah, that now looks okay. We have a leg from the last hour, a leg from the last day, and a leg from the last week. In this case, both from consumption and production. Yeah. Usually we do like an 80-20 test split in machine learning. I most of the time hope to have more than 1 year of data, because then what we do a lot in these kind of time series is we have 1 year of training and 1 year of testing, because then the model has seen every season and every month of the year. In this case, because we only have 1 year, I kind of do a 50-50, because sort of assuming that it then has seen some summer, some autumn, and some winter in the training. And then there's some winter, some spring, and some summer in the testing. But if we assume that spring and autumn are kind of similar, then we've seen similar stuff in the training and testing. But you can also play around if you get different results if you use a way shorter or way longer training period. But yeah, in this case, I start so the start is in June 2021, training ends last day of the year, and then the first day of 2022 we start testing, and we end testing in May of 2022. Yeah, this is the only part I got to delete something. We want to predict the consumption, or you can also try to predict something else, and you can pick now here which variables you want to use in order to predict the consumption. So you can, for example, put in the last day of the consumption, and then just add all the variables you think that we already have that are useful, or create new ones if you feel like it. Yeah, just make sure that for the train and the test, it's the same set.
So when you look at the system, you mentioned that when you have a spike in energy production, but it's better to consume.
Yeah. There's no storage. So in this system, there's no storage. Most households don't have storage. And for most households, it makes no sense to have storage at the moment. It's mostly too expensive, or they would have to be really, really large to get back the investment you put in. But that might also change. They're getting cheaper year by year. Now you feed it back into the grid, so someone else can use it. But you can't, in Germany, unfortunately, at least, it's not allowed to just share that electricity with your neighbor. That would be awesome. So you just feed it back into the general electricity grid and hope someone else needs to use it. Then if everybody does that at the same time, that would mean that you could not use a gas power plant, for example.
If you would get money back, you would actually could say that the money would be stored.
Yeah. You get money back, but I think at the moment it's something like it costs 42 cents to buy electricity, and you get 8 cents if you feed it into the grid. So
That's the wood counter which my parents had, then the counter can go backwards.
yeah, there in other countries there's also the system that instead of you getting money for the electricity that you feed in, basically your meter that records how much electricity you've stored just goes backwards, and then you have to pay less. Then it's the exact same price. But yeah, in Germany you need to have a really, really, really old contract to be allowed to do that. Other countries do this as their default. Yeah, if you selected your features that you want to include, you can run the next step where we just have a simple linear regression model. Also just using the sklearn package, not implementing it ourselves. And I've plotted the test data. And you can see that at least with the variables that I picked, I severely underestimate the consumption, but the pattern is there. So it gets sort of the general idea, but underestimates the consumption quite a lot. And just to store all the results, I'm starting here a data frame that we add on rows while going through the notebook. One other thing that for consumption can be quite cool to have as features is something like which hour of the day is it? Because if we know it's 12 noon, that helps us. If we have the lag from exactly 1 day ago, that already covers this feature a bit. And the other part is like, is it a weekend or not a weekend? That for most, also industrial consumption makes quite a big difference. Because especially neural networks can't really deal that well with dummy variables, so like lots of one-hot encoded variables. One way to encode the hour is these sine waves. You can also do a mixture of sine and cosine, so that this tells the network or the linear regression that after, in this case, 24, we start again at 1, and that there's not a difference of 23 between the value 24 and 1, but like it's the next value. Yeah, that's just one of the interesting things here. And then we can use the same features as before, but also include some of these time features and then hope that it actually got a bit better. So yeah, in this case, it just got very, very marginally better, but a tiny bit better at least. Has anyone put in features that are better than these ones? Okay. Yeah, in the C section, all that happens is that we train a neural network, and we do that in this case using PyTorch. So there's a bit of voodoo of reshaping the data in a way that you can feed it into PyTorch. It's basically meaningless apart from the fact that you put it into the shape that PyTorch can work with. And then we just, for all the neural networks following, we've normalized the data. That helps the networks a lot. For the linear regression, it usually makes absolutely no difference. but the neural networks perform a lot better when the values are in an equal range. Yeah, and then it is choose neural network architecture block. You can, I have a super simple network. It has a linear layer, a ReLU activation function, and another linear layer with like 100 hidden neurons. So it's smallish, and that is kind of chosen by random. So you can also play around with it and see what happens when you change these parameters, add layers, add hidden neurons, remove hidden neurons, and so on. And if we train that, and hopefully trains very quickly, and we can plot what's going on. And if you have a similar model like I put in, that's super simple. This is the result of a vanilla stupid neural network. As you can see, that's very terrible. So we get the mean right, and that's about it. Yeah, to be fair, we have not included any of the features. I've only included basically what's the consumption and what's the time. But what I wanted to show you a bit is that just because you use a neural network doesn't make it suddenly magic and can do the stuff that you want it to do. So if you do a very naive neural network, you get a terrible result. And then we can add more features. I've commented this out again. So basically in this calls to include, you can put in the names of the columns of the data set that you want to include, and I will just copy it from above if I find it again. Here we are. And then the rest is again, so whenever it says float tensor or something, torch dot, it's just data wrangling so that PyTorch can handle it. We normalize the data again as before, and then train the network this time with more input. So we see that the network number of parameters already increases and it's already slower. But this time it actually looks like a reasonable result. So it's very similar to what the linear regression does in the sense that it performs a bit worse with respect to this pure score or the average score, but it gets the general pattern very well, but it underestimates the consumption. And in this case, it also gets quite some below zero values, which for electricity consumption is impossible. You can't have negative electricity consumption. Okay, because we're almost through time-wise, you can just, I think there's nothing missing in the following block. So you can just, this is a complex recurrent neural network. And we can have a look at how this performs with the same set of parameters now. The code, I think, should also run on a GPU. Somehow my notebook has not connected to one, but if you connect to a GPU, it's a bit faster. Ah. Oh yeah, sorry, I forgot to say that. So if you just follow the link, you'll end up at exactly this notebook. And if you want to play around, yeah, good thing that I say that 1 hour later. You best save a copy in Drive or wherever you want to save it. Or just highlight everything and copy paste it to a notebook. If you change something in this notebook, then it changes it for everybody. But I will put a clean version up after, maybe later tonight, so you have a clean version available, hopefully.
It says cannot save changes.
Ah, okay, awesome. Then I just hijacked the. That's okay. It'll be fine. So yeah, with the, if you run the LSTM model the way that I put in the features, then this looks again very, very similar, but we have none of the weird zero values now. So this is a lot better than the naive version of the network, with regard to just how intelligent it is. And we are only slightly worse than a linear regression, but it took us like 5 more minutes or something, plus coding this more complex model. And the last method that I've implemented, or the last 2 methods, are a decision tree and a random forest. So a decision tree is a single one of these. A random forest are multiple of these, where you basically just decide at each node, for example, should I go swimming today? Is it sunny? Is it not sunny? Is it okay? Is it sunny? Is very cloudy? A little cloudy, raining, and then you go through this tree and come to your decision. And you can, instead of doing that with categorical features, you can also do that with this regression. Even if you give out this tree, you can't really make much out of it. But interestingly, the predictions are really, really good. And in this case, the random forest prediction is marginally the best in our use case.